She's in second period. Okay, so this is Coulomb's law. So 2 weeks ago we discussed static electricity and electric charge and force. Wednesday we did some activities to help you understand the concepts better. So we did stuff with pith balls and electroscopes and the comb and bending of water. So today we're going to be talking about how to find the magnitude of the force if you have 2-point charges. So up to this point we've just been talking about the phenomenon that's occurring, but not actually how to figure out the magnitude of the force. So we can do this by using Coulomb's law. So from the video we just watched, the definition of Coulomb's law is the magnitude of the force between two charges. So we're going to call these charges QA and QB. And they're separated by a distance. We call this D. That the magnitude of the force, it's proportional to the magnitude of the charges. And it's inversely proportional to the square of the distance. So this definition might be kind of scary or really long sounding, but it's just a formal definition. It's actually pretty simple. So if you have an object with mass, if you have two objects with mass, there's usually a force of attraction between them. So if you have two charges, we can use Coulomb's law to find the equation to find the electric force between them. So the equation for Coulomb's law equation is the electric force, so that's F with a little subscript E, is equal to the electric constant, which is Ke, or in your book I believe it just has K, times QA times QB divided by the distance between A and B squared. So you can say Q1 and Q2 if you want. It's just, I find it easier to use letters than numbers because you have a lot of little numbers in your equations, so it makes it easier to keep track of what's going on. So this is the equation you're going to be using for all your homework assignments the rest of this week and next week. So Ke, this is just the electric constant. And it's a constant of nature, so that means it never changes. And this value, we'll give you this on a test. It's 9 times 10 to the 9th newtons per meter squared over coulombs squared. So there's a new unit for you. C, that is coulombs. And charge is measured in coulombs. So on your homework problems it might say like a 6 coulomb charge. That's just the units that they use, coulombs. So the definition says the magnitude of the force between the charges separated by a distance d is proportional to the magnitude of the charges. So that just means that if we have a bigger QA, your force is going to be bigger, and if you have a bigger QB, then your force is also going to be bigger. So the opposite is true with saying that it's proportional, inversely proportional to the square of the distance. So what we just watched in the video, he went through the inverse square law. So the further apart it is, the weaker the force. So if you're 3 times further away, 1 over 3 squared would be 1/9 as strong. If you're 10 times further away, 1 over 100, that's 1/10 as strong. So for example, Pluto is 35 times further away from the sun than Earth. So on Pluto, 1/35 squared, that's the strength of the rays of the sun reaching Pluto compared to on Earth. So the further away you get, the weaker it gets. So that just explains that definition. It's not super scary when you break it down. So I'm going to draw 2 pictures for you. You're going to be using these on your homework, or you should use them. So we learned, or you should know from chemistry, that if you have similar charges, they're going to repel. So here I have 2 positive charges. So I'll label this one charge A. This one is going to be charge B. And there's a distance between them. It's labeled D. So they're repelling. They're applying a force on each other. So this arrow represents the force of charge A on charge B. Force is a vector quantity. And over here, this is the force of charge B on charge A. And this would be similar if you have 2 negative charges. This diagram is also in your book on page 472. If that helps you better, you can look in your book, and it has the same drawing. Okay, so now we can also do it for opposite charges. So here I have a positive charge. Here I have a negative charge. So I'm going to label this one charge A. This is charge B. So now they're attracting. So the arrows are turned in on each other. So this is my force of charge A on charge B. And over here is my force of charge B on charge A. Because they're pulling each other, they're attracting, so they're pulling each other together. So when you do your homework problems, you're going to be needing to use these 2 pictures to determine the direction of the force. So make sure you reference back to these. So that's basically all you need to know to solve our homework problems. I'm going to do 2 example problems for you. That'll help you out. Okay, so just so you know, so we already know that force is a vector quantity. With charges, sometimes they have positive and negative signs, but in the Coulomb's law, you don't use the sign. So it doesn't matter if it says negative charge. To find your force, there's no positive or negative. It's always going to be positive, I guess, if you're using positive, because we're finding the magnitude of the force. You only use the positive and the negative when you're finding the direction of the force. So that's where it plays in if it's a positive or negative. So we'll start with example number 1. And in your book, this is on page 474. And it says that 2 charges are separated by 3 centimeters. Object A has a charge of positive 6 times 10 to the negative 6 coulombs, while object B has a charge of 3 times 10 to the negative 6 coulombs. What is the force on object A? So this is example problem number 1. So your first step is to draw a picture. So here we have positive charge A, and we have a positive charge B, and they're going to be separated by a distance. Here's the distance between A and B. So we were given, let's write out your givens. Charge A is equal to positive 6. The subscript is called micro coulombs. It just stands for 10 to the negative 6. Just a shorter way of writing it. When you put it in your calculator, you still need to write out 6 times 10 to the negative 6. And then we know charge of B, that's positive 3 microcoulombs. And the book told us that our distance between A and B was 3 centimeters, so we need to convert that to meters. So that just gives us 0.03 meters. So they're asking us to find the force of charge B on charge A. So to solve, we can use Coulomb's law. So we can say the force of QB, or charge B on charge A, is equal to the electric constant times charge A times charge B divided by the distance between A and B squared. Then we can go ahead and plug in our numbers. So from our notes above, the electric constant is 9 times 10 to the 9th newtons per meter squared over coulomb squared. Then that's times 6 times 10 to the negative 6 coulombs times 3 times 10 to the negative 6 coulombs divided by the distance squared, so 0.03 meters squared. When you plug that into your calculator, we find that the force of charge B on charge A is equal to 1.8 times 10 to the second newtons. Then your last step is to figure out the direction of the force. So they're similar charges, they're both positive. So you can look back on what we drew earlier over here. So it ends up, shows us here, the charge of B on A is going to be to the left. So over here, if we have, sorry, can't see, object A, this is my force of charge B on charge A. That's the direction. So this is the direction of the force. Of charge B on charge A. Are there any questions on example problem number 1? It's pretty simple once you break it down into the different steps. You just need to make sure you draw a picture first, make sure you label the charges correctly, and plug it into your calculator in the correct order. Because you only times it by the electric constant after you do this part first. Okay, so now we're going to move on to example problem number 2, which is more involved and a little bit harder, but it's not too bad. You're not going to see anything that hard on your homework, but I just want you to know how to do it, and if you understand it, it's going to be very helpful for future problems. They wouldn't ask you something this hard on the state test. Okay, so example problem number 2 is on the next page in your book. on page 475. And it says a sphere with a charge of 6 microcoulombs is located near two other charged spheres. A -3 microcoulomb sphere is located 4 centimeters to the right, and a 1.5 microcoulomb sphere is located 3 centimeters directly underneath. Determine the net force on the 6 microcoulomb sphere. So first we're going to want to draw a picture. So here we know that we have charge A, and that's positive. We're going to make this our x-axis. This is going to be our y. It's just for reference. Okay, so we have charge A, and next to it is located 4 centimeters to the right is another charge. This is our -3 microcoulombs charge. This is going to be, I'm going to label this charge B, and that's negative. And the distance between them, I'm going to convert to meters. It's 0.04 meters away. And located 3 centimeters directly underneath is a 1.5 microcoulomb sphere. This is also positive. This is going to be my charge C. And the distance is 0.03 meters away. So if you look at this, if you remember from trig or geometry, if I drew a little line here, this could be a triangle. So that means that we can use the Pythagorean theorem to solve this problem. And the tangent function, yay, everyone loves doing that. Okay, so now we're going to move on to our given. So now we have our picture. It's going to be really helpful later. So given QA 6 microcoulombs. Just going to write it out for you. QB is -3 microcoulombs, and QC is 1.5 times 10 to the -6 coulombs. And then we know the distance between A and B, 0.4 meters, and the distance between A and C, 0.03 meters. Now we're asked to find the net force. But to find the net force, we're going to need to find the force of B on A and C on A, and use the Pythagorean theorem to find the net force. So our first two steps are to find force of B on A and the force of charge C on charge A before we can figure out our net force. So now we can go to solve. I'm going to solve for the force of charge B on A first. So we just set it up the same as we did on the problems before. So the force of charge B on charge A is equal to the electric constant times charge A times charge B divided by the distance between A and B squared. So if you plug in your numbers, that's just 9 times 10 to the 9th newtons per meter squared over coulombs squared times our 6 times 10 to the -6 coulombs times 3 times 10 to the -6 coulombs. Remember, we're not using the negative sign because that plays in with the direction of the force. Right now we're just finding the magnitude. Then we're going to divide by 0.04 meters squared. And when you plug that into your calculator, you should get 1 times 10 to the 2nd newtons. that is our force of charge B on charge A. And then we need to find the direction. So again, we can look back on this picture from earlier, except this time they're opposite signs. So the direction of the force it is going to be to the right. Okay, next we can do force of charge C on charge A. And we're just going to do the same thing. So we have our electric constant times charge A times charge C divided by the distance between charge A and charge C squared. Then when you plug in your numbers, that's just 9 times 10 to the 9th newtons per meter squared over Coulomb squared. That's just times 6 times 10 to the negative 6 coulombs times 1.5 times 10 to the negative 6 coulombs divided by 0.03 meters squared. When you plug that into your calculator, you end up with 90 newtons. And these are both positive charges. So because they're repelling, the direction of the force is up. Because they're both laying on the y-axis. Okay, so you're 2/3 of the way done. So we can head back up here and add to our picture. So our force vectors. For charge B on charge A, it's to the right. And force of charge C on charge A is up. So when you add vectors together, our net force is going to end up being somewhere in between these two. So there's an angle here that we're going to need to find. And how can we find that? By using the tangent function. So we can say that the tangent of theta, if you remember SOHCAHTOA, opposite over adjacent, we can use this formula, which is just the force of charge C on charge A over the force of charge B on charge A to find that angle. So when you plug in your numbers, it's just 90 newtons over 1 times 10 to the 2nd newtons. And you end up getting theta is equal to 42 degrees. So that is the direction of the net force. It's 42 degrees above the x-axis. So this angle is 42 degrees. So you can always find the tangent angle before or after you find the net force. Either way, we already found the two main components to solve for the net force, so that's why we can do either step, whatever order you feel like doing them in. So now is the easiest part. We're just going to use the Pythagorean theorem to find the net force. So if you remember, c squared equals a squared plus b squared. So we can say our net force is equal to the square root of 1 times 10 to the second newtons squared plus 90 newtons squared. And that gives us 130 newtons. So the net force is 130 newtons, and the direction of the force is 42 degrees above the x-axis. So those are just 2 example problems of how to solve using Coulomb's law and find the magnitude of the force between 2 and 3 point charges.